Hello, my topic for assignment 2 is GNN for credit card fraud detection. I chose this topic because credit card fraud detection sits at the intersection of graph structured data, unstructured data mining, and deep learning, which are topics that genuinely interest me. What drew me in was realizing that most people frame fraud detection as a simple classification problem. They look at transaction, decide if it's fraud, but that misses something fundamental. Transactions don't happen in isolation. Every purchase connects a cardholder to a merchant, to a bank, and that relational structure is rich with information. On top of that, most contextual data like transaction text, location history, behavioral patterns is unstructured, and traditional systems throw all of that away. That felt like a significant and addressable gap, which is exactly what motivated this report. When I surveyed the existing literature, I noticed each method solves one piece of the puzzle but misses the others. Classical ML is well established but blind to both graph structure and unstructured data. Fraud NLP showed that transaction text carries genuine fraud signals but treats each user in isolation, missing coordinated fraud across accounts. Graph-based models like GNN model relationships well but ignore unstructured data entirely. The closest to my proposed approach was Liu et al., who combined LLMs with GCNs, but their decoupled training means that the text encoder has no idea it is feeding a fraud detection graph, weakening the overall framework. That's when it became clear the gap wasn't just one thing, it was the combination of heterogeneous graph structure, rich unstructured features, and causal reasoning trained jointly end-to-end, which is exactly what this framework addresses. Okay, so here's the proposed pipeline. The core idea behind this framework is bringing everything together in a way that no prior work has done. That is, instead of treating text encoding and graph learning as a separate disconnected steps, we train the entire framework end to end, meaning every component learns to work together towards the same goal of detecting fraud. For a transaction text, I chose BERT specifically because it is a transformer-based model designed to capture contextual relationships in language. Because we train end-to-end, the BERT encoder doesn't just learn general language representations, it also learns text representations that are specifically used for fraud detection in a graph context, meaning like urgent overseas transport would mean different than Netflix subscription. For GPS location traces and behavioral logs, I chose LSTMs because both of these are ordered sequences that change over time, and the order and timing of events matters enormously. For example, a sudden geographic displacement between transactions or an unusually rapid sequences of logins and purchases are exactly the kinds of temporal patterns LSTMs are designed to capture through their memory mechanism. And the graph itself is modeled as a heterogeneous with relation-aware attention, meaning a cardholder to merchant purchase age is treated differently from a cardholder to bank transfer, allowing the model to learn distinct patterns per relationship type rather than treating all connections equally. Finally, the causal reasoning component addresses something I found particularly compelling, which is the camouflage problem. So basically what it means is fraudsters sometimes deliberately connect to legitimate users to blend into the graph. Without causal reasoning, a GNN would dilute the fraud signal by averaging over all neighborhoods, including those innocent connections. The causal mechanism separates genuinely suspicious neighbors from spurious ones, making the model significantly more robust and against sophisticated fraud strategies. Okay, so I modeled this as a heterogeneous graph rather than a homogeneous one because cardholders, merchants, and bank accounts behave very differently, and so treating them as identical nodes would lose that distinction. The three distinct relationship types, purchases, bank transfers, and merchant settlements, will allow the model to learn different patterns per relationship rather than collapsing everything into one generic connection. What makes this powerful is that it captures both relational structure and unstructured context simultaneously. For example, a cardholder suddenly transacting at merchants in a completely different geographic location is a signal that spans multiple entities and transactions, something a traditional transaction by transaction system would never catch. Only a graph representation can surface that kind of cross-entity pattern. To wrap up, this framework treats credit card fraud detection as what it fundamentally is, a graph mining problem over rich unstructured data. Future work will explore federated learning and fairness auditing before real-world deployment. Thank you.